Hello, everyone. Welcome to our second walkthrough on cryptography. The last session was last week, where we covered some of the easier challenges. If you missed it, uh, please go view the recording before you watch this series, because there is some knowledge you may require from the previous session. These sessions are part of our AspireCTF walkthroughs, which we have been running over the past few months. And we've been viewing them from the point of view of the creators to show you how they could have been solved and also to give you the perspective of the intended solutions, although there may be alternate solutions. So I am CK. I was the one who created the cryptography CTFs. And so I will be taking you through these challenges. We still have a few more to go. So ensure that you subscribe if you want to be notified, and keep track of our social media channels, and you will be able to view or be notified of our upcoming walkthroughs. Uh, so again, we will be hosting other related sessions, both as ICRAL and both as the Aspire team. There is the Cybersecurity Awareness Month currently ongoing. We will have a CTF soon in collaboration with one of the communities locally. So keep a lookout for that too. So without much ado, I'll start the walkthroughs. Today's will focus mostly on breaking codes. So a lot of the previous one was introductory to show you how cryptography works, simple ciphers, the Caesar cipher, the exalt ciphers, and so on and so forth. So today we are actually going to go into the challenges that required you to break codes. And there's going to be a lot of technical information. The whole point will be to give you the information and the knowledge behind these attacks. And we'll also cover some code that you can use to do this. Another thing is that these challenges were pretty difficult. So we usually have beginner to intermediate, but for the cryptography, we also included some pretty difficult ones. And the intention was that you will find these attacks in real world systems even today. So these are actual vulnerabilities that are in use or you will find in use in your applications. So they will also be very helpful in how you implement your cryptography or your cryptographic functions. So let's begin. So let me share my screen. So the first one we will start with was a challenge called one way. And the question was break the following hash. Then there was some hash that was provided and we were given the flag format. So again, this is the hash. I've pasted it here for easy access. And what we can immediately tell from the challenge is that based on what the flag is going to be, we have been given a hint in that the length of the flag in between the curly brackets, we have 4 question marks. That means that we have 4 unknowns. So that helps us narrow down the correct flag. The other thing we can figure out is that the hash is most likely going to be MD5 based on the length of the hash and based on the fact that it is alphanumeric. So MD5 hashes are usually 32 characters and are alphanumeric. SHA-1 and SHA-0 are usually 40 character, but there are ways you can identify hashes based on their length and the type of characters that they contain. So for the flag, we can see that if we were to count the total number of characters, this would be 15. And we already know, let me confirm that. No, it's 12 actually. These are 12 characters. We already know 8 of them. The only ones we don't know are these 4 that are included in this curly brackets. So trying to crack passwords that are 12 characters in length, even if it's an insecure hashing algorithm like MD5. MD5 is currently considered broken. So ideally don't use it in any applications that are security conscious. So use more modern hashing algorithms. I would say go to at least SHA-256 to be safe. But even for MD5, if you have 12 characters in length, it's still going to take you a long time to crack a hash. In our case, the good thing is, as I said, we already know 8 of the characters. We only need to find out 4. So what we will do is we will generate a word list that has all the possible variations of these characters. And there are several tools you can use, but one I usually like is called Crunch. So if you have a Debian-based system like Ubuntu, Kali Linux, you can install it using the inbuilt package manager. In my case, I would use apt. I already have it installed, so it should be pretty quick. Then the next thing is, what we will do is we will generate a word list based on what our expected flag is. So if we come, let me explain what the flags mean. So this 12 and 12 mean minimum and maximum length of the password. So in this case, it's 12. Then we are going to cover all alphanumeric, numeric, and we are going to cover the alphanumeric key space in short. Then we are going to save them in the file called wordlist.txt. And this here explains to Crunch where we want to generate the characters. So by specifying this @ sign here, we tell it we only want to generate these variations here. So this is what is going to be replaced as we generate the word list. So we are going to have a lot of aspires with different values in between the curly brackets. So there are various ways you can use Crunch. This is just an example. So you can exploit. It's very useful for a lot of custom password cracking exercises. So once I run this, tells that it will generate this number of lines. So this is around, is this 81 million lines? So that is complete. Shouldn't take too long. So almost done. So you aren't limited to tools like Crunch. You could even write a script to do this for you, for those who are good at scripting. So it's already generated this. Let's see what has been pressed in that file. And as you can see, this is what it has done. It's taken what we provided it and we told it to generate variations of these characters in between the curly brackets. So again, this is useful if, let's say, you know someone uses an insecure password that starts with certain letters. Let's say password 01, password 02, password 03. You could use a tool like Crunch to generate all possible variations. Like this will have Aspire with all of the possible variations of 4-letter, a 4-character length in between the brackets. So with that, you can use various tools to now crack the hash and recover the flag. There are tools like John, Hashcat, and so on and so forth. But for this case, I used a custom script I wrote in Python. It's called MD5 cracker. So it's pretty simple. So this is just a library to help us with some functions. Then we are going to open our word list. We specified the hash. Then we are going to calculate the MD5 of every line in our word list, then compare it with our hash. If they match, we know that we have recovered our flag. So you don't have to use Python, but it's usually a pretty easy language to use, and you can quickly script these things. So if I then run my cracker and give it a few minutes, or let's hope it doesn't take too long, it will run through the word list and give us our flag. When it runs, I think let's go back to our challenges. So eventually it should give us this flag called Aspire, and in between the curly brackets was the word nice. So this was the flag. Hopefully this won't take too long. I don't think I have timed it yet. So let's see. While this runs, if you have any questions, you can ask them on the YouTube chat. You can ask them on our social media channels and any other form of communication that we use. Then we will respond to them either during the walkthrough, or you can even ask specific questions and we would respond to you directly. So let's see. There are faster tools you can use for this, like Hashcat. Hashcat uses GPUs for cracking passwords. You can use multiple cores to, if your processor has multiple cores, you can use various tools to speed up this process, but I'm just doing this on my laptop, so it isn't going to be that fast, but the password isn't that complicated, and we should have the result pretty soon. So I'll leave that running and start talking about the next challenge, then we'll come back to this. So the next challenge was called Breaker, and it was single byte exalt. And the message was, the following hex encoded string has been exalt against a single character. Find the key and decrypt the message. So this was hex data. If you copy the hex data, this was what was provided. I think it moved out of the page. So this is the total, this is the full length of the data. And we've been told that this has been encrypted. So in short, this is the ciphertext, and we've been told to provide the flag in this format. Aspire and then have the first line of the message in between the brackets to provide our flag. So before we start on that, yep. And as you can see, the password has been cracked from the previous challenge. So I think we can close this and move on to now this new challenge. So for this one, there are two approaches we can use to solve it. So first of all, we don't know what the key is and we don't know what the message is. We only have the ciphertext. The good thing is that we know it's a single character that has been used to exalt the data. So that already gives us some information. If it wasn't, the rank wasn't known, it would have been a different approach, which we'll cover in one of the challenges as we move along. The first method is called the chi-squared test. So in code breaking, the chi-squared test is used to compare how closely related are plain text. Plain text is the original data. The original unencrypted data closely resembles the encrypted data. So when you exalt a character, one character with another, let's say in our case, we are using one single byte. The new exalt character will provide the ciphertext. So the comparison between consecutive characters, let's say if I exalt A with a single byte, what we get is a new byte. If I exalt B with another, with the same key, which is a single byte, I should get a different ciphertext byte. But the two will be related because A and B are closely related. They only differ by one bit. So if, as I said, if I exalt a B with a single character, the resulting ciphertext will be closely related. It will also differ by one character. So what the chi-squared test does is, if I exalt a certain sentence, what will result as a ciphertext will have the same distribution as the plain text. So how the chi-squared test is used to do this is, we will try to decrypt the ciphertext with all the possible single character bytes, then compare the similarity of that ciphertext with what we would expect a normal distribution of plain text to be. So how this is possible is based on how languages are structured. For instance, the English language is structured in such a way that we know that the most common character is most likely going to be the letter E. So in a normal sentence in the English language, you're likely to find a lot of E's. And then you're likely to find very few Q's. So if I write a whole sentence, the probability of finding E is usually around 12%. So if we take our ciphertext and decrypt it with various random bytes, then we compare the distribution of E's. If those E's approach 12%, we know we have a high probability of that being the correct decryption. So first of all, let me show you what I mean. So I have a file that has the probabilities of you finding certain letters. So the probability of finding an A in a ciphertext is 8.55%. As I said, A is usually the most common. So if, let's say, any random sentence, the likelihood of finding an E is 12%. The likelihood of finding a Q is 0.1%. So using this, we can base this, you use these relationships to try and guess what the plain text is. So again, as we said, languages also have relationships between pairs of letters, because like the letter TH, it's very hard to find the letter TH in the combination of T and H in sentences. They, them, they, and so on and so forth. So again, for more complex challenges, you may have to use those relationships. Like in this case, this gives you the probability of finding certain combinations of letters. Like TH, this is 2.71, HE 2.33, and so on and so forth. Some are very low. As you can see, let's see one of the lower ones. Like the probability of finding ET is much, much lower than the probability of finding TH. So that's what enables us to break down some of these ciphers. It's usually called frequency analysis. So the frequency of E is very high, the frequency of Q in any random sentence is very low. So again, if we go back to the chi-squared test, what it will do is we will try to decrypt the ciphertext we've been given using all possible bytes. All possible bytes would be the 256 possible bytes. There are 256 possible bytes that we can use to decrypt. So once we decrypt, we will compare that, the probability, the number, we will count the number of E's in that decryption. Do they approach 12? So that's what the chi-squared test does. And there's a formula for it that we usually use it. So how the formula works is we usually take C, which is the count of a certain letter. So let's say we decrypt the ciphertext with a random byte, and we find that we have 10 A's. We will take A as, that will be our 10 here. Then we will minus the expected number of A's in a normal ciphertext. In our case, we can say the expected numbers of A are 8.55. So that's what we would use as our E here. Then we will again divide by that same 8.55. This up here would be squared, and so on and so forth. So this is again a snapshot of the number of the distribution of letters in the English language. This is for the English language. So what we will do is we can script this whole thing. We take the ciphertext, try to decrypt the ciphertext with all possible bytes. Then we compare which one most commonly resembles what a normal English sentence would look like. So as I said, there are two methods. You can just use the chi-squared test. There's another rudimentary method you can use to do frequency analysis, but for now, let's use the chi-squared value. So this is basically Python. Python is usually pretty easy. So I don't think you really need to cram what the code does, but get the idea of what it's doing. So as I said, some of the most important parts are this. This is used to calculate the chi-squared value. And as you can see, this is the same formula we have here. So what we are doing is we will try various decryptions, and the frequencies we are going to use are these ones, the ones I opened for you in the terminal. This is exactly this here. This is what we are going to base our counts on. Then again, we are going to decrypt using all possible bytes. So as I said, the range of bytes is 256. So it's from 0 to 256. So we are going to decrypt using all possible bytes. Then we are going to calculate the chi-squared value for all possible decryptions. And the lowest value is what usually gives us the most probable message. So at the end, we'll print the correct message. So again, eventually we will share these walkthroughs, this code and everything. And if you have any questions or you need more in-depth explanations, we can either plan very specific questions for very specific areas, or we can answer your questions directly. So let's run this challenge. So in this case, our encoded string was this. And it will print the correct key for us, which was this 91, and now gives us the decrypted message. So, and our flag was supposed to be the first line of the decrypted message. So this was supposed to be what our flag was. So this is exactly what we have done here. So again, frequency analysis. I said you can use the chi-squared value, or you can use just regular old mathematics. So what we do in a normal rudimentary frequency analysis is, once we decrypt, we try to decrypt the ciphertext using all possible 256 bytes. Then for every decryption, we count the number of letters that we expect. In our case, the letters we expect are here. All lowercase letters A to Z, all uppercase letters A to Z, a space. And so, yeah, these are the most common things you'd find in the English languages. All the letters, both lowercase and uppercase, and probably spaces, because the English language uses spaces. Then what we are going to do next is we are going to calculate how many of these letters we can find in all the possible descriptions. The one that has the most letters is likely going to be our decryption, because if you decrypt the ciphertext with another random key that isn't the correct key, you are likely to get letters that are not ASCII characters. So you're likely to get a lot of UTF-8 characters not in the ASCII range. So this is a basic way you can use to do frequency analysis. So decrypt the ciphertext using all possible bytes, then calculate the number of letters that you would expect in a normal sentence. So if the sentence has all letters and all spaces, it's a high probability that it's a correct decryption. So again, that's an option we could have used. So there's the chi-squared test, and there's just the old traditional way of doing frequency analysis. So again, if you run this, it also gives us the correct flag. So with this, if you've gotten that fundamental knowledge, then even cracking the rest of the some of the other challenges becomes a bit easier, because it's going to be key in solving 2 or 3 of the coming challenges. Next one was a bit harder, but same concept. It was called breaker, single byte exalt in a haystack. So it says one of the 94 character strings in the attached file has been encrypted by a single character exalt. Find it and decrypt it, and you've been told to provide the flag as shown. So if you open the file, the text has these several lines that have all been encrypted using a single character exalt. So we don't know which one is the one that has been encrypted. That's why it's called single byte exalt in a haystack. So one of these several strings is the correct encryption. We don't know which one. So first of all, we need to figure out which one it is. Then also figure out what the correct decryption is. So good thing is, this is if you've solved the previous challenge, this is just about whether you can write an algorithm to do this. So what we would do in this case, we can still use both the chi-squared test or the frequency score test as in the previous challenge. But what we are going to do is we are going to start with one line here. We are going to pick one line, then solve this as if it was the correct line that we are supposed to decrypt. So we would take this, run it through all the 256 possible decryptions, then find out if what is it called? The chi-squared score is matches what we would expect in the English language. Then if it matches, we have a possible solution. So we would store that possible solution somewhere. In coding, we usually use arrays to store data. So arrays help you to store huge amounts of data that you can compare with. It's like some form of structured storage. So if you've coded before, I think you already know what arrays are. So we'll take this, deal it with it directly, try to decrypt it with all possible 256 bytes, calculate the chi-squared score, look for the most likely candidate and save that candidate as a possible solution. Then once you're done, go to the next one, repeat that, go to the next one, repeat that. So at the end, we would have an array with all the possible decryptions. Then to find out which of all the decryptions is correct, then we can, I would say, use the frequency score to determine which is the correct one. So again, we are going to actually combine the chi-squared score. For the first part of each one, each possible decryption, do the chi-squared score. At the end, we have an array of all possible decryptions that have already been passed through the chi-squared score. After that, we use the frequency analysis to again find out of all the possible decryptions, which is the most accurate. So we can even go through the code. So again, we read the data. Then after we read the data, again, we have the function to calculate the chi score. We have a function to do our frequency score. Again, we have our file that has the expected frequencies of a normal plain text in the English language. So the first thing we do is we create an array that contains the ciphertext. Then we'll try all possible decryptions and save the possible decryptions in the array. Then we'll compute the chi-squared score. And from there on, then we can try to figure out which best matches our matches the English language. Again, as I said, the one with the lowest chi-squared score is going to be the proper candidate. So again, this is going to be recorded. If you need to go back and refer to something, or probably even refer to the previous challenge where I've tried to explain what the chi-squared score does, then you can do that too. So if we run that again, it should give us our flag. So again, there are various ways you can code this. You aren't limited to Python, but Python is usually one of the easier languages to do this. So next one is, again, a bit harder than the previous ones. This one is called repeating exalt. It's also a breaker challenge. And we have the challenge asking, the hex encoded data in the file attached has been exalt using a repeating key exalt. Find the key and decrypt the message. The key length is between 2 and 20 bytes. The flag format is Aspire, then brackets, then the key in between. And we've been given a hint which says Hamming distance. So for this challenge, this one becomes a bit trickier. The reason for this is we don't know the length of the key. We've been told it's between 2 and 20 bytes. So we can't just go and try a frequency analysis or the chi-squared test, because again, for that to be successful, we first need to know the specific length. So it becomes a bit harder. So the first thing we would need to do is figure out what the key length is. And that's where the Hamming distance comes in. So there are various references you can use to guide you on what the Hamming distance is. But in short, it's used to, it's a calculation used to compare different data and figure out what is different between the two data sets. So let's say I have hello and hello. Hello has an A, hello has an E. The difference between the two is the A and the E. So that's just one difference. In regular use, the Hamming distance is usually used for error correction. So let's say I send you a message. The Hamming distance is used to determine whether the message got to you without any errors. Because if there are any errors, the Hamming code distance would be higher. So the more the variations, the higher the Hamming code distance. So mostly when we are using it in cryptography, we deal with bits. So that's binary data, and we compare the bits that are different. So let's say 1001 and 1000. There is one difference. So I think during the last session, we covered a lot of CyberChef. So I'm going to show you how you can use CyberChef to calculate the Hamming distance. There's a recipe called Hamming distance. So CyberChef is a tool by GHCQ. Usually can access it online or even host it on your own. So there's a recipe called Hamming distance. So let's say I compare these two strings here. As you can see, the difference is just this last byte here. So the Hamming distance would be a 1. So let's say I change another bit. You would see that the Hamming distance becomes 2. You can even do this for, let's say, regular English words. As I said, hello and hello. As you can see, the difference is A and E. So the Hamming distance is 1. So how would the Hamming distance help us determine the length of the key? For this, there is someone who wrote a very good article. I think this is the best explanation I could find, and I would encourage everyone to go through this post. So this is the post, nayak.io. So it's called What's So Special About the Hamming distance. And first of all, there is an explanation about what it is. As I said, it's the differences between two data sets. In this case, the data in red is what is the difference. So we can see it's 4 because it's 4 separate points where the data is different. So how is it useful? So let's say we encrypt, in this case, the word that they are encrypting is full-bar-go, and they've used this key. So if they encrypt this using a repeating key exalt of rank 3, so it would repeat after every 3 characters. So as you can see, the first 3, it's these 3 that encrypt the full. Then for the bar, it would also be encrypted by, again, the repeating key here. And the final part would also be encrypted using the same key. So this is a repeating key exalt. So, and this would be the result. So to decrypt this again, we would first need to know the key length. as we have been asked. In our case, we've just been given the ciphertext, but we don't know the length. In our case, if we didn't know the length, we could try and calculate the Hamming distance of data and figure out what the length is. So how we would calculate the Hamming distance in cryptography is we usually exalt two data sets, and then the differences is what gives us the Hamming distance. So in this case, what he has done here is he's going to start with possible key size guesses. So you can start with the lowest key size you want to guess. Let's say in our case, we were told that the key size is between 2 and 10. So we would start guessing 2, a key size of 2. So in this case, if you go to the ciphertext, this is the ciphertext, you would separate the first 2, and if it was a key of length 2, this would have been encrypted using the key, this would have been encrypted the key, and so on and so forth. So if we were to divide this into 2, the Hamming distance we would calculate would be between these two parts, these 2 bytes and these 2 bytes, and so on and so forth. If we are trying to determine if it's a key length of 3, we would use these 3 bytes and these 3 bytes again. So again, this is what he has done exactly here. So he's divided the data into groupings based on what the key size is that is to be guessed. So in this case, the Hamming distance calculated here is 8. But again, remember we are using different key sizes. So to ensure that the data is normalized, we usually divide that by the key size. As in our case, the key size is 2. So we divide it by 2 to get 4. For this one, for a key size of 3, the Hamming distance is again 8, but if you divide by 3, that becomes 2.67. So again, there are tools to calculate the Hamming distance. I've just shown you the CyberCTF tool. You can script it as I will show you in the script that I use, and so on and so forth. So as you can see, in the end, the Hamming distance of 3, the key size of 3 produces the lowest Hamming distance if you compare all of them. This is 4, this is 2, and this is 4. So this helps determine that the key size was 3, which is accurate based on where we started here. So why does this work? So as I said, it's all based on what we expect when we exalt data sets. So if I exalt ABC, I expect the resulting ciphertext to also be 3 characters that follow each other, or 3 bytes that I'll differ by one bit each. And that's how the English language is structured. It's A to Z, and they all follow each other. So A, B, C, D, E, F, and so on and so forth. Each one is 1 bit higher than the other one. So it isn't really random. So the lower the Hamming distance, the less random that data is. So there's a lot more technical explanation here, but if you do want a better explanation, again, we can have a full session where you cover just the Hamming distance. But the thing is, if we exalt 2 data sets of the English language, we expect the Hamming distance between them to be very low, because the English data set has characters or commonly used characters that are within a very short range. They aren't that random. So if it was a higher Hamming distance, it would mean a greater disparity between two data sets. So if, let's say, I exalt ABC with XYZ, the Hamming distance for that still wouldn't be that high. It's within the ASCII key range, so the Hamming distance would be very low. But if I was to exalt ABC with bytes that aren't within the ASCII range, then I would expect the Hamming distance to be much higher. In short, the differences between the two would be much higher. So that's how the Hamming distance helps us determine the key. So if we choose the correct key length, the Hamming distance would give us our possible key length. And that's what we do here. So once we have the Hamming key length, the rest is easy. We've already done it using the previous examples. We can use either the frequency score or the chi-squared value to, again, decrypt the data. So as you can see, the challenges became more complex as you moved on. And these are actually attacks you can apply on real-world systems. A lot of malware others use exalt to encrypt their data. So you don't know what the key is, you don't know what the key length is, and so on and so forth. But using these attacks, you can actually decrypt that data without necessarily knowing what the key is, what the key length does, and so on and so forth. So again, that's why we made these challenges a bit harder to make them practical for your everyday use. For developers, again, it gives you a chance to see what could go wrong. Just exalting your data with a random key doesn't make it secure. So in this case, the major thing we needed to do here was the Hamming. So this is how we are calculating our Hamming score. So again, don't worry too much about this. You can code this in any language, but in my case, I'm using Python. So don't want to start explaining the Python language, but what we do is we'll take a range of, actually I used a possible length of 2 to 41. The question asked for 2 to 20 bytes, but that would have been enough. But in my case, I used possible lengths of 2 to 41. Then I calculated the Hamming lengths of all those possible lengths. Then the one that had the highest score was the key length that was the most probable candidate. So after calculating that Hamming length, we print the candidate here. Then from there on, it becomes a simple solution of now decrypting the key, figuring out what the key is using frequency analysis or the chi-squared value. Don't want to repeat that again since we've already gone through that. So this is just the Python code to do that. Again, we'll share this code. And should you have any follow-up questions, or should you want to, or should you try this and you want to figure out what was happening somewhere, we would be happy to have a follow-up sessions or even provide specific help in what you needed help in. So again, if I run this, so let me show you. First of all, we calculated the hanging distances. So as you can see, these were calculations of the Hamming distances of the possible lengths. So once we had the possible lengths, we had the lowest Hamming distance. I think, can we find it just visually here? Actually, I think I had grouped them. Yeah, it's already sorted. So this is the candidate with the lowest Hamming length. So we actually know that the key length is 7. So we also recovered the key using the frequency score or the chi-squared value. Once we recovered this key, the next thing was just to decrypt the data. And For this, the flag was supposed to be Aspire, then the key. The key is Ririco based on our solution here. So that was a solution to this. Again, cryptography, some of these challenges may look a bit intimidating, but once you get the hang of it, you don't have to get it at the first go, but the important thing is to get the concept of how you break these codes and other techniques you can use. Nowadays, we are fortunate we can use languages, algorithms, computers. Previously, you mostly had to do a lot of this using paper, pen and paper. The earlier code breakers used pen and paper, especially if you follow the code breakers during the First and the Second World Wars. You would find that they used a lot of these techniques in their actual code breaking techniques. So I think finally we'll go to a different type of challenge. I would say pay specific attention to this one because this is something you will see in a lot of applications in even today. It's based on AES. AES is considered one of the safest ciphers to use currently. It's recommended by standards and so on and so forth. But if you do it wrongly, it can still be broken. So what we did is we actually implemented a system that encrypts your data using AES 128 ECB, just like a normal system would. And we asked you to crack it. So for this one, I'll show you how, if it's not properly implemented or just a normal regular implementation can be cracked and someone can be able to decrypt your data without even knowing the key. So the challenge was this. The Aspire cryptographic system accepts your input and encrypts it as follows. So it takes your string. So you provide a string, it concatenates it with a flag. So once you provide it data, it appends the flag to your data. And in that case, after that, it encrypts the data for you and gives you the result. So you don't know the key, you just send data to the system, and the system encrypts the data and shows it back to you. So for instance, if you input 1, 2, 3, the system will add the flag to the data, encrypt it, and then show you what the encrypted data is. So this is something that normally happens. Let's say you are encrypting data that you know always has a specific section added to it. Let's say username. Okay, let me give you an example. Let's say I have a system that whenever I encrypt the data, let's say it's even a banking application, it adds the, before it saves the data, it adds the word, what's a bank's name? Bank one. Then I send it a username. Then it probably says user one, then encrypts this data. Then user two sends their data, and then the system takes the data and says bank one, user two, then user three sends data to it. It uses that data as, or it can even be the reverse. You send data to the system, then user one it appends the word bank to it, and then encrypts this data. Then user two, it adds this data to it and encrypts this data. So in this case, this value here is controlled. I can send any value to it because if I register as a random user, let's say register a name user 20, it would be appended to the data like this. So ideally, this is the type of system we are trying to break. So if our flag is 1, 2, 3, and I send data to the system, what it's doing is, let's say I send, let's just call the flag flag. If I send the characters 1, 2, 3, it will add 1, 2, 3 to it, then encrypt this, then store the data and decrypt it and show me the encrypted data. So I don't know the password, I don't know the flag, but it shows me the encrypted data. So how do I break this system? This is in essence what the challenge was. So this is an attack that you can actually use in real world attacks. So first of all, let's just connect to, before we even go to how to break it, let's just connect to this and see how this is going to work. So once you connect to the system, this is what we get. Welcome to the system. To encrypt the data, enter the word encrypt and the data. So if I say encrypt 1, 2, 3, it just gives me the encrypted data back. So what this means is it's taken my 1, 2, 3, added the flag here, and encrypted the data, and then showed me the encrypted data. So I don't know the key, and I don't know what the data is. All I can do is send it data, and it encrypts it together with the flag. So if I encrypt that, again, this is the data that gets back to me. So as you can see, it's very different data. So how do we break this system? So the attack is called byte at a time decryption. So let me explain the logic. So again, when you send an input to the server, the input is appended to the secret. In our case, it's the flag. So here it's our flag. And then the server encrypts it, and then the server shows us the resulting encryption. So block ciphers usually are based on certain lengths of blocks of data. So there's a block length of 8, a block length of 16. The most common is 16. 16 is usually a safe bet, but you could code this in such a way that your algorithm can try to determine the block. There are ways to do this. We aren't going to cover this here, but if you want a session on how you can detect the block length of a cipher, it's another thing we can cover. So how do we break this system? So the first thing we are going to do is we are going to try to decrypt the first message of the flag. So let me do this. So let's say we have a flag called ABCD. So if we have a flag called ABCD, how do we start trying to figure out? We send our data to the system. So let's say we send 1, 2, 3. The system takes this, encrypts, does the encryption and sends us back the encrypted data. So how do we break this? So what we would do is, first of all, if the block length is 16, which is the most common, what we would do is we would first, let me see, I think I've expanded this too much. Let me reduce it. So we know this is our flag. We don't know it yet. We don't know what the key is, but we can send any data to the server and it will prepend it. So the first thing we can do is determine the block length. Let's say the block length is 16 as is most commonly used. I don't know why my editor is misbehaving. So what we would do is, if the block length is 16, we would first send a stream of data, random data of key length -1. Let's say if it's 16, we would send 15 characters. If we send 15 characters, what the server would do is it would append our flag to it. Okay, let me use X's. 1, 2, 3. Let me do 15 of them. So if I send this to the server, what it would do before it encrypts the data is it appends the flag, then encrypts this data and sends it back. But we know it's a block length of 16. So if we sent it 15 X's, it would take this first 16 and this is what it would then, it would be the first part of the encryption, because block ciphers, ECB specifically, it's called the electronic code book mode. Will split their data into the block length and encrypt those blocks. So it would take this, encrypt it, and show me a ciphertext. So if I was trying to guess what this character was, I would send this, I would take all possible 256 bytes. I would send this, see what ciphertext I would get. Let's say I get some target ciphertext here. Then I would also take this again, but this time I would append B instead of A. So again, I would get some ciphertext. This is just some ciphertext too. Then I would also do this again and send it with a C. So what we are trying to do is trying to figure out if we can identify what the byte is that follows our data. So if you are following through, what we would do whenever we send this, what would be encrypted? What would be encrypted would be this. It would encrypt this, then append our flag. So it would append this, true. Then if we send this, this is what it would do. The server would do this, then append this. If we send this, it would also do that, then append this. So how do we figure out what our correct character is? So in all of these situations, we can see once we send just this 15 here. So let's split this into 2. So the very first time we send 15 characters. So this is 15 characters. For block ciphers, it would need 16 characters to create the first block. So to create the first block, it would append A, B, C, D, which is the flag, and show us the ciphertext for this. If we send it this with an A, now this is 16. It would again, it needs 16 blocks. It would still append the flag, but what it would provide for us would be this. I think you can already see that what it would provide us is exactly what was here when we just sent the 15, because this is similar to the first byte of the flag. But if you had sent a B, what it would encrypt would be this. Now this would be a different key. It would not a different key. It would provide us with different ciphertext. Again, if we sent this, as you can see, the first 16 wouldn't match with what would be the correct flag. So let's say we solve that. We know our first character is A. We've cracked the first byte. So after that, we would send now 14 bytes. So we would send 14 bytes. If we send 14 bytes, what would the server do? It would append our ciphertext. So it would do this. It would append A, B, C, D and create some ciphertext. Then after that, okay, let's call this our target ciphertext. This is our second target ciphertext. If we send this now, again, remember this is now 14. What it would do, it would take the first 16. And so we know this target ciphertext is an encryption of, with including the first two characters of our key. As you can see, it's taking the first two characters of the flag. Again, we would repeat the same process, but in our case, we already knew that the first character was A because we figured out that at the first time. So we'd take that, do this, then append the first possible decryption, which is AA. Then again, we would take this, then send the second one, and so on and so forth. So if you are following here, you can see that this ciphertext, this is also a ciphertext. As you can see again, it's taking the first 16. If we check this, this wouldn't match with our target, which is the first 16. But this one here would match with our ciphertext here. So we would already recognize that the second character is B. Then we would do the same for the third one. We know the second one. Now we would take the first 13. We'd send 13 of them. What would the server do? The server would append the flag. The flag is A, B, C, D. So again, it would need 16. It would take the first 16 since it's a block length of 16. So that is what it would encrypt, and it would show us this target ciphertext. So that is our third target. Then, as usual, we already know what the first two are from our previous session. So the next one, we would send what we already know, and then we append the first possible byte. That would be a ciphertext candidate. Then again, we can repeat this we would do this for all possible bytes. So the first one was A, second one would be C, that one would be D, and so on and so forth. So if we keep sending all of them, we would get one that matches what our target was, and it would be this one. So again, we would figure out that the third character was C. So if we keep doing this all the way to the end, we would get a decryption of the full message without knowing the key, but just by an algorithm and playing around with how block ciphers work. So this is just how they implemented. This is a vulnerability in implementation, specifically the AES ECB mode. So hopefully you've been able to follow how we are doing this, but we're going to do it practically with our challenge. So let's do it practically now. So the first thing we do is let's connect to our system. So once we connect to our system, again, we are going to send it with 15 X's. So let's start there. So ideally, what happens when we send 15 X's, it will append our flag here, then encrypt the message for us and show us the ciphertext. So we know that the first 16 bytes, which should be somewhere, these are hex. So anyway, I'll show you that if we copy this, I think I had already copied it here. This would be the first block being encrypted. So we know that our flag has been appended here. So we know the first character of the flag is included here. So what if we send this again? Now we append an A. So if you append an A and check the ciphertext, we see that we have received the same exact ciphertext for the first block, and I have copied it here. So if you compare the first block here and this first block here, you see they are very similar. This is an indication that the first character guess of A was correct, because if we had sent a B, you see the first block has changed completely. So that means that it doesn't match our target ciphertext, which was the first block. So we would try for this for all possible 256 bytes. Since we already figured it out from the very first A, which was a lucky guess, luckily for us, we don't have to go through all the 256 because we have already found a matching one. So we've already identified the first byte. Now to identify the second byte again, we would now send 14. Same logic. If we send 14 bytes, we now again have a new target ciphertext that we would use. We know that when we send 14 bytes here, it's already appended our flag here before sending us this back. So we know there's an A here because we already know what the first byte was. We know there's an A here, but we don't know what the second character is. But we know for the first block, this first block includes this plus 2 bytes here. It's 14 plus 2. We already know the second one was going to be A. So if we send this again, we know the second one is definitely going to be an A. We discovered it from the first attempt. Then we start guessing what the second byte could be. Could it be an A? And we see that we have a completely different first block from what we are getting here. So we know the second one can't be an A. So if we do this again and say, could it be a B? Again, very different first block. So we can do that again. I think I copied the wrong thing. Let me just, where is this one? Here. Could it be a C? Again, what we'll compare, remember we are comparing it with the one we sent with just 14. Because for this one, we are sure that it appended 2 of the correct characters, which are our flag. So we continue guessing until we get to the one that is correct. So we would go this for all possible bytes. And in this case, the next one would be I know the correct one, so I won't go through all of them. I know the next one is going to be S. So if I do that, then compare this with this, we can now figure out that we've identified the second byte of the flag. Next thing, we would send 13 instead of 14 of them. So this is, you can do it by hand if you wanted, slowly but surely, and finally figure out what the flag is, because in this case, we already know what the first two characters are. So if we add A and S and a third character here, the one that matches this would be our third character. In our case, I already know it's P. So as you can see, they match. Any other one wouldn't match. So that's how you progressively decrypt the encrypted passphrase without knowing the key or interacting with uh, the plain text. So all this is good, but the problem with this is it would take too long to do this by hand. So again, use Python. We can code this. Again, this is an explanation of what is happening here. As I showed here, we've gone through this, but to do this, we can continue this whole process until we decrypt the full message. So for this, there is this code here that automates the process for you. Again, it just does that. It's just that it's automating that process. So won't dwell too much on the code. But if you want, you can try actually writing it yourself to do that logic. But if you need help, you can still contact us and we would be happy to help. So in this case, I have, it's going to be pretty slow because it's going to be best guessing, going through this whole process for all possible 256 bytes until it identifies a character, then goes on to the next one. So let me run that. Then it's going to start listing them one by one as it identifies them. So it's identified the first one as A. So it's the same thing I was doing here. It's just that it's been coded to make it more efficient and faster. So as you can see, it's going to do this until it gives us the full flag. It's actually going a bit faster than I thought it would. That's the good thing about code. You wouldn't have to do this all by hand. Like here, it's taking a bit longer because the next one is a curly bracket. And before it gets to that guess, it's a lot further down the line than the normal alphabet, then, but it's gotten it. So we aren't going to wait for the full, it was a pretty long sentence, so we are going to leave it running, but we will share the walkthrough, we will share the code so that you can also experiment with it yourself and also try to modify it. Maybe you can make it faster and so on and so forth. But eventually what we get is this flag here. And that was the correct answer. So again, don't worry too much about not getting every specific detail, get the concepts. And with that, you will be able to even identify vulnerabilities in other different implementations, because there are a lot harder challenges out there. There are a lot harder ways you can break codes. And a lot of these challenges can be gotten on a site called cryptopals.com. They have a lot of challenges on cryptography where they take you from the basics all the way to much harder ones. So if you want to test yourself with some of the hardest challenges you can do, from the simplest to the hardest, to ones that are being discovered currently, I would suggest go through all this. They start you with the basics where you learn how to do the basics, just like we did in the very first walkthrough. So that should cover our walkthrough for today. I know it's a bit intimidating and a lot more technical than usual. So I hope you are able to at least gain some knowledge, some insight. And again, if you want follow-ups, if you want more challenges, uh, please feel free to contact us and we would be happy to assist. Cryptography is an interesting field. People usually are afraid of it because of a lot of the mathematics involved, but once you get a hang of it, it's pretty interesting and fun to break codes and figure out how to protect them. So again, it will be recorded and you can view it on YouTube. We have a couple of more sessions remaining. I think it's either 2 or 3. We still have to cover network security monitoring. We have mobile security. We have reverse engineering. So keep checking our various platforms and you will be notified on when we will have those walkthroughs. So thank you everyone for joining and see you next time.